Right now, astronomers are staring at data from the James Webb Space Telescope, expecting answers but encountering puzzles that rewrite cosmic history. The most powerful telescope ever built was supposed to clarify the early universe, but instead, it's created problems we never saw coming. 3 discoveries that are so puzzling have emerged, forcing scientists to question everything we thought we knew about how the cosmos began. First, JWST found far more massive galaxies than theory allowed. Next, it spotted heavy elements appearing too early in cosmic history. Finally, it revealed mysterious little red dots that defy our models. These discoveries aren't minor quirks. They challenge our fundamental picture of how galaxies and elements formed in the universe's infancy. Too many cosmic giants. When astronomers first opened JWST's images of the distant universe, they knew something was seriously wrong. Where sophisticated computer models predicted they'd find perhaps a handful of faint, early galaxies scattered across vast space, JWST revealed massive, blazingly bright galactic structures everywhere they looked. The shock wasn't just that these galaxies existed. It was that there were so many of them, shining with an intensity that shouldn't have been possible when the universe was barely starting. For decades, astronomers have relied on a simple principle. Brightness tracks stellar mass. More stars, more light. So counting bright galaxies shows how fast mass assembled early on. Ground-based telescopes and Hubble spent years mapping this relationship, creating a reliable framework for understanding cosmic evolution. Every major simulation of the early universe was built on these observations, predicting that bright, massive galaxies should be extremely rare in the first few 100 million years after the Big Bang. Then JWST started taking data, and those predictions crumbled. The telescope was finding roughly 10 times more bright galaxies in the early universe than any model had anticipated. These giants appear 400 million years after the Big Bang, containing billions of stars, when the universe should have allowed for 1 or 2 generations of star formation. It's like finding fully built skyscrapers on an empty construction site. That's the level of surprise astronomers experienced. These impossible galaxies don't just exist. They're thriving. Some show evidence of containing stellar masses rivaling modern giant elliptical galaxies, but compressed into a cosmic time frame where the numbers don't add up using conventional stellar physics. Several competing theories have emerged to explain this abundance. First, hyper-efficient star formation. Perhaps the early universe's extreme conditions allowed gas clouds to convert into stars at rates far exceeding anything we observe today. Second, a top-heavy initial mass function where the early universe favored forming more massive stars, which shine much brighter than typical stars, creating the illusion of more stellar mass than exists. Third, extra light from early black hole accretion. We're actively feeding supermassive black holes add significant luminosity through their glowing accretion disks. This discovery fundamentally challenges our understanding of dark matter halos, the invisible scaffolding that galaxies form within. If these bright galaxies are as massive as they appear, dark matter is assembled into galaxy-sized clumps much faster than current physics allows. The universe would have had to hit the ground running in ways that break our established models of cosmic evolution. Astronomers are now conducting intensive spectroscopic campaigns with JWST to determine whether these are truly massive galaxies or elaborate optical illusions created by exotic physics we don't yet understand. Could the early universe have flipped our rules of star and galaxy growth? JWST's next spectroscopic surveys will try to find out. But the telescope's surprises don't end with oversized galaxies. The atoms inside them reveal their impossible secrets, elements that shouldn't exist. JWST is detecting heavy elements like oxygen, carbon, and even iron in galaxies that formed when the universe was supposedly too young for these elements to exist in such quantities. Carbon and oxygen appear in galaxy spectra just 350 million years after the Big Bang, when theoretical models suggest these elements should be virtually undetectable. This creates a fundamental problem because it contradicts everything we know about how the cosmos builds complexity over time. The cosmic timeline of element creation tells a clear story that starts with the Big Bang, which produced only hydrogen and helium. Everything heavier had to be forged inside stars through nuclear fusion. Massive stars spend millions of years converting lighter elements into heavier ones in their cores, then scatter these newly created elements across space when they explode as supernovae. This process requires multiple generations of stars, living and dying, to build up significant quantities of heavy elements in any galaxy. We spot elements by their unique absorption and emission fingerprints in a galaxy's spectrum. This technique has been reliable for decades and forms the foundation of our understanding of cosmic chemical evolution. JWST observations show these heavy element signatures in concentrations far higher than any simulation predicted for such early cosmic times. These aren't trace amounts that barely register in the data. These are substantial quantities that indicate active heavy element production on a massive scale. Recent claims of iron detection in early galaxies have made the situation even more perplexing. Finding iron so early, when models say it takes many stellar generations, suggests cosmic enrichment that should have taken billions of years was compressed into a few hundred million. This has created what astronomers call the chemical evolution problem. Several solutions have emerged to explain this rapid enrichment. Pair instability supernovae from extremely massive first-generation stars that could rapidly disperse heavy elements across space. Binary star systems producing more frequent white dwarf collisions that create iron and other heavy elements. Or extraordinarily efficient early star formation that compressed millions of years of normal chemical evolution into much shorter time frames. Which of these scenarios, if any, can match JWST's data? The possibility that early star formation operated under entirely different rules connects to broader questions about whether the early universe's extreme conditions enabled physics processes we have never observed in the modern cosmos. These observations are forcing astronomers to question whether the early universe followed fundamentally different rules from what we see today. But JWST's most confusing discoveries might not be massive galaxies or impossible elements. They might be tiny objects that look utterly ordinary until you examine them closely. The crimson Enigmas. These compact red objects scattered throughout JWST's images look deceptively simple, but turn into complete contradictions when astronomers analyze them in detail. At first glance, these little red dots appear straightforward. Tiny red points of light that suggest compact galaxies dominated by older, cooler stars, similar to the ancient elliptical galaxies we see in our local universe today. Their red color and small size initially made perfect sense to astronomers who expected early galaxies to be compact and filled with aging stellar populations. But spectroscopy tells an entirely different story. When astronomers split the light from these objects into its component colors, they discovered spectra that show a puzzling dip in visible light, bracketed by strong UV and infrared, something no known galaxy produces. This dip, called a Balmer break, usually signals ionized hydrogen from hot stars. Yet these dots lack the usual dust that would obscure UV light. Physics doesn't align with astronomers' stellar evolution and dust formation knowledge. JWST's instruments detect warm dust emission in some of these dots. Yet the UV light shines through unblocked, an uncanny mismatch. This dust should absorb and scatter UV light, dimming it substantially. But the spectra show strong UV emission anyway. The dust is there, the instruments confirm it. But it's somehow not doing what dust usually does in galaxies. The leading idea is feeding supermassive black holes with light-producing UV without the expected dust absorption. Evidence lies in broad emission lines, indicating gas roaring around massive centers. The material spiraling into these black holes forms accretion disks that become extremely hot and emit intense radiation across the electromagnetic spectrum, including the UV light the JWST observes. These extreme velocities suggest material orbiting something with an enormous gravitational pull, consistent with actively feeding supermassive black holes rather than stellar processes. Alternative explanations involve exotic stellar populations or unusual dust geometries that could create the observed spectral features without invoking black holes. Some models propose that these galaxies contain unusually high proportions of very hot, massive stars, or that dust distributes itself in ways that don't obscure UV emission as expected. Whether it's black holes or bizarre star formation, these crimson enigmas reveal the early universe played by its rulebook. The little red dots force astronomers to consider that early cosmic conditions might have enabled physical processes we have never observed in the modern universe. These three discoveries, the massive early galaxies, the impossible heavy elements, and the mysterious red dots, point to the same unsettling conclusion about our cosmic models. What we see represents a fundamental shift in astronomy, from confirming predictions to grappling with observations that challenge our most basic assumptions about cosmic evolution. We're witnessing science in real time as astronomers work to understand whether these discoveries require new physics or simply reveal how extreme conditions in the early universe pushed familiar processes to their limits. From Chile's deserts to space-based observatories, astronomers collect every photon JWST can deliver. Scientists worldwide are racing through follow-up observations and refined simulations to crack these mysteries. Solving these puzzles will likely revolutionize our understanding of how the universe transformed from the simple aftermath of the Big Bang into today's complex cosmic web. If you're as fascinated by space as we are, you won't want to miss these other videos. We dive even deeper into the universe's secrets and explore recent discoveries that could revolutionize your understanding of the cosmos. Thank you for joining us on this cosmic adventure. Stay curious and keep looking up.